Welcome to this online training about external memory interfaces in Intel Agilex devices. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. The main objective of this training is to get you familiar with the parallel external memory interface options available in Intel Agilex FPGA devices and how to implement them in your designs. You'll learn about the architectural features available in Intel Agilex devices that implement memory interfaces. The architecture is different from previous device families, so it's important to understand the underlying architecture to see how everything works and how external memory interfaces are built. You'll then get familiar with the design flow for the memory IP for these devices, named Altera EMIF FM. This includes simulation, timing analysis, and using debug tools to verify the correct operation of an interface. Here's the full agenda for this training. The second part covers the design flow for adding the Altera EMIF FM IP to a design, the options available when parameterizing the IP, and the required design constraints. Subsequent parts of this training, available on the Intel FPGA training website and linked at the end of this training, discuss how to verify and debug an Altera EMIF FM implementation. As mentioned when you register for this training, it is highly recommended that you have previously watched the first online training listed here, or have experience with implementing external memory interfaces in other FPGA devices. The first online training linked here goes into detail on the basics of external memory and implementing memory interfaces in older devices that use the UniPHYIP IP and the high-performance memory controller. The second linked training discusses memory interfaces in Intel Cyclone 10, Intel Aria 10, and Intel Stratix 10 devices. It builds on the information presented in the first training. There are some similarities in the EMIF implementation between the Series 10 devices and Intel Agilex devices, but the architecture and capabilities are different enough that this training is your best resource for an Intel Agilex implementation. For more detailed information about all aspects of the memory IP and implementing a complete memory interface, see the External Memory Interfaces Support Center and the Memory IP user guides available there for each device family. It's a good idea to always have the EMIF IP user guide for your targeted device available. They are the definitive guides for every aspect of creating a memory interface using an Intel FPGA and will be referenced throughout the training. Once again, here is the recommended design flow for creating a working EMIF interface. In this part of the training, we'll walk through the process of parameterizing the memory IP and adding it to an Intel Quartus Prime project. We'll also look at resource management, including how to share resources between multiple interfaces. Now that we've looked at the EMIF architecture and how memory interfaces are built, we can look at the main memory IP, called Altera EMIF FM, and the required calibration IP, named Altera EMIF Cal, and how to add them to a design. To create a memory interface, you use the Altera EMIF FM and Altera EMIF Cal IP cores from the Intel Quartus Prime IP catalog, or add them as components in a platform designer system. Unlike previous memory IP, where there were separate IP for each memory protocol, there is only one for Intel Agilex devices. The memory protocol is instead set as a parameter for the IP. Altera EMIF FM provides a complete solution for the main interface in a single IP. Along with Altera EMIF FM is the calibration IP. This required IP is used to connect one or more memory IP to the I/O SSM block for a particular I/O row. So, at most, you'd have two calibration IP in a design. A single instance of the IP calibrates all the memory interfaces in the top or bottom row of the device. If you are familiar with the older memory IP that consisted of UniPHYIP and the high-performance memory controller, you should appreciate many of the new features and improvements found in Altera EMIF FM. First, the new IP generates very quickly, usually in much less than a minute. The new IP can perform automatic I/O-related assignments, setting options like termination and I/O standards without having to run a separate Tcl script. The design flow for creating and using the example design generated by the IP is much more flexible and customizable. When the IP is generated, a customized datasheet is included, providing information about the IP, as well as next steps for using it in your own design. As mentioned earlier, the OCT block is now part of the hardened resources, so it is no longer necessary to make connections to it in your RTL code. Other improvements included simplified file sets for both synthesis and simulation, better simulation accuracy and speed, improved simplified timing analysis, and an improved EMIF toolkit for analyzing the calibration of the interface. If you have previously added the UniPHYIP IP to a design, the parameter editor for Altera EMIF FM is very similar. In the next few slides, we'll highlight some of the new or different options available. To simplify things, we'll focus on parameterizing the IP for DDR4. Parameters may be different for your targeted memory protocol. Be sure to check the IP user guide for details for your particular setup. We'll start with the General tab in the IP parameter editor. As mentioned earlier, the memory protocol itself is now a parameter for the IP. This parameter can be set or changed at any point. In the interface section, if your selected memory protocol supports it, choose whether to use or bypass the hard memory controller. In the clocks section, set the full rate clock frequency of the external memory and the reference clock frequency. It is recommended that you have an oscillator on your board that can supply the recommended reference frequency. However, you can disable the checkbox and select from a list of frequencies that will work with the PLL. No matter what frequency is selected, the external oscillator on your board must supply the selected frequency. Set the clock rate of user logic parameter appropriately. As listed earlier, the IP can automatically handle the transfer of data between the memory clock frequency and the internal user logic running at a fraction of the external frequency, either a half or a quarter. Setting this to quarter simplifies time enclosure. The core clocks sharing option is used to share clock networks between multiple memory interfaces. We'll look at clock networks and other resources that can be shared when implementing multiple interfaces later. Finally, you can enable an option to have the IP output up to 4 additional clocks from the IP's PLL for use elsewhere in your design. You can customize the properties of these clocks once you enable the option shown here. These clocks are considered separate and asynchronous to the memory interface's clock domains. The Memory tab is very similar to the settings found in the older UniPHYIP IP. The basic parameters of the external memory are specified here, along with a variety of other options depending on the memory protocol selected. Examples include the physical memory format, either individual components or a DIMM, the row and column address widths, and CAS latency settings, including the enabling or disabling of additive latency, as discussed earlier. The Mem I tab is used to specify additional settings for the external memory's mode registers, focusing on the memory's I/O pins. Specify the memory's output drive strength and on-die termination, or ODT options, including whether ODT should be enabled or not on reads and writes. Like the FPGA's OCT options, the memory's ODT options are based on an RZQ resistor connected to the memory. On the FPGA I/O tab, you can set the general I/O standard for the interface and select separate I/O standards and other parameters for different signals in the interface. The options available depend on the type of memory being accessed. You can also specify what the series and parallel termination options should be for OCT for the different types of signals based on the value of the RZQ resistor you've connected to the interface. You can use all the default values, but if your board design is unusual, such as using a different characteristic impedance, or you want to guarantee that your design meets signal integrity requirements, you'll need to simulate your design in a board simulation tool and adjust the parameter values listed here appropriately. We'll talk more about the need for board simulation in a moment. As with previous IP, the Memory Timing tab is where you configure all the timing parameters for the external memory based on the memory's datasheet. New options to take note of are the base AC and DC level options. In the previous IP, some memory timing parameters needed to be derated to take into account slew rates across the board. The slew rate information was set on the Board Settings tab in the UniPHYIP IP Parameter Editor. Here, the datasheet values along with the derating value are all set on the Memory Timing tab. This makes it easier to correlate between the datasheet values and the derated values. When entering values from a memory datasheet, be sure to enter the timing values based on the part binning, not the speed at which the interface will run. In other words, if, for example, you're using a faster speed memory part that can run at up to 1066 MHz, but you'll be running the part at only 533 MHz, enter the timing numbers here for the 1066 MHz part, not for the slower part. Timing parameters that should be based on the speed you are running the memory and other factors are located in their own sections at the bottom of the tab. Here are the timing parameters to adjust based on your use of the memory instead of the part binning. As mentioned earlier, DDR4 supports slow or fast timing requirements depending on whether you are successively accessing the same or different bank groups. Set the values for these requirements, named TRRD, TCCD, and TWTR here. You can also set the refresh cycle time, TRFC, and the average periodic refresh interval, TREFI, based on the density of the external memory being used. The next tab is the Board tab. However, board-related parameters have been removed from the IP as of version 19.3. In previous iterations of the IP, board-related parameters were used only when performing timing analysis, not for adjusting the actual hardware implementation of the interface. However, it's critically important in the process of designing a board to follow the guidelines described in the EMIF IP User Guide, and to perform board simulations and analysis before, during, and after production to ensure the design meets timing and signal integrity requirements. For more information on board design and simulation, besides the EMIF IP User Guide, see the linked articles on the Intel FPGA Wiki. The Controller tab provides options for how the hard memory controller will operate. At the top of the Efficiency section, you can enable complete user control over all refreshes issued to the memory. This is done through the Memory Mapped Configuration and Status Register Interface, or MMR, which must be enabled in the Configuration Status and Error Handling section below. Enabling the User Refresh Control option requires the user logic to issue adequate refresh commands to maintain memory contents. Also in the Efficiency section, you can enable Auto Precharge Control to have the controller issue auto precharge read and write commands instead of separate time-consuming precharge commands after a read or write. You can also choose how addresses should be mapped between the local interface and the external interface. This option is usually based on whether sequential data, random data, or sequential data with multiple chip selects will be transferred across the interface. For 3DS DDR4, the address ordering also includes the chip ID, or CID, for choosing a particular memory die in the 3D stack. See the EMIF IP user guide for details. You can also enable or disable command data reordering. You can also add an additional top-level control signal that can be manually asserted to indicate a high-priority command, overriding the built-in reordering algorithm. In the Configuration, Status, and Error Handling section, more options are available here that are similar to previous memory IP. Enabling the MMR interface exposes an additional Avalon slave interface that gives access to the settings and status registers for the memory interface during runtime, including the ECC logic if that option is also enabled here. ECC requires a memory interface that is 16, 24, 40, or 72 bits wide. Finally, the options in the data bus turnaround time section allow you to insert additional clock cycles when bus turnaround events occur, such as when performing a read immediately after a write, or vice versa, within the same rank or between different ranks. Adding additional cycles may help resolve bus contention issues. In most cases, though, leave these settings at their defaults. The next tab is the Diagnostics tab, which is, again, similar to the settings for the older UniPHYIP IP. Many of the options here are for simulating the design and for debugging a design running on a board. In the Simulation Options section, choose whether to skip calibration when simulating the design, or simulate the full calibration process. Simulating memory calibration can take hours, so it is recommended in most cases to skip it for simulation. Calibration debug options allow for the use of the EMIF debug toolkit or the on-chip debug port for analyzing and debugging memory calibration issues. These settings have been moved to the separate Calibration IP, which will be discussed in a moment. Further down on the Diagnostics tab is the Example Design section that includes debugging options for the example design you can create for the IP. We'll discuss example design creation in a moment, but the number of core clocks sharing slaves to instantiate option refers back to the option on the General tab about sharing the core clock networks among multiple memory interfaces in the same I/O row. This option allows you to choose how many of the interfaces sharing the clock network should be included in the example design. You can also enable the In-System Sources and Probes debugging feature for the example design. This option is required for using certain features in the EMIF debug toolkit, such as analyzing margin on the example driver. We'll look at the EMIF debug toolkit in more detail in the on-chip debugging online training. The traffic generator section lets you further customize the example design. Coming in a future version of the Intel Quartus Prime software, the Avalon Traffic Generator 2.0 is a configurable and controllable traffic generator created in FPGA soft logic for sending data patterns to the external memory for simulation, testing, and debugging. The current traffic generator IP performs a fixed sequence of write and read commands for testing the interface. Traffic Generator 2.0, or TG2, can create completely custom patterns, controlled with either a simulation script, the EMIF debug toolkit, or custom logic. Enabling the efficiency monitor adds an additional Avalon slave interface to the IP for analyzing the efficiency of the controller. The EMIF debug toolkit works with this to provide statistics on the efficiency of the memory interface. Again, see the simulation and debugging online training courses for more details on these features. Finally, in the miscellaneous section, you can choose to export the PLL's lock status signal to the top level to verify PLL lock. At this point, you can generate the EMIF IP standalone. We'll take a look at generating a full example design in a moment. As mentioned earlier, Altera EMIF FM can be generated with either the IP parameter editor, accessed from the Intel Quartus Prime software IP catalog, or in Platform Designer. Let's look at generation with the IP parameter editor first. When Altera EMIF FM is generated, a number of files are created in the locations specified. First, a .ip file is generated. This file stores all the selected parameter settings and is used to reopen the parameter editor for the IP if any of the settings need to be modified. Also generated is an instantiation template and an example top-level HDL file to make it easy to create a new project for the IP or to add and instantiate the IP in an existing design. Next, a customized datasheet for the IP, mentioned earlier, is created in a subfolder of the variation name folder. This is a simple text file with customized information about the parameterization of the IP, along with instructions for next steps in the design flow. The main files that define the IP are found in the same folder. As with other IP, you can choose to create files for synthesis, simulation, or both. Files for synthesis are placed in a synth folder, while simulation model files are found in a sim folder. All of these files are pointed to by a single .qip file found in the variation name directory. The .qip file is the only file that needs to be added to the Intel Quartus Prime project, if it is not already added to the project at generation time. This .qip file not only points to all the IP files, but it includes all the I/O-related assignments for the IP. Previously, a separate tickle script needed to be run to add these constraints to the project. The new format of the .qip includes the constraints without having to run a separate script. Before discussing the creation of an example EMIF design, it's important to look at the calibration IP, which is required for any EMIF implementation. The calibration IP is added as a separate instantiation or platform designer component and is configured through its own IP parameter editor. The available parameters are shown here. Since the calibration IP is responsible for calibrating all memory interfaces in an I/O row, the parameters for it reflect the calibration options available. Set the number of calibration interfaces to the number of interfaces that need calibration in either the top or bottom I/O row. Choose whether to skip calibration when simulating the design or simulate the full calibration process. Simulating memory calibration can take hours, so it is recommended in most cases to skip it for simulation. The EMIF Debug Toolkit on-chip debug port option must be enabled in order to use the EMIF Debug Toolkit or on-chip debug port for analyzing and debugging memory calibration issues in a single row of the device. See the Debugging Memory Interfaces online training, linked at the end of this training, for more details. While you can manually instantiate and connect the calibration IP to one or more instances of the memory IP, the easiest way to connect them together is to add them as components in a platform designer system. In the example shown here, the calibration IP has its number of calibration interfaces set to 1. The memory IP has conduit and clock interfaces specifically for connecting to the calibration IP. The IP are connected together as shown. If more than one calibration interface is enabled on the calibration IP, connect the single clock from the calibration IP to all memory IP instances, but connect each calibration conduit interface to a single memory IP's matching interface. If you create your own complete design, you have to manually add and connect the calibration IP to it, as just discussed. However, if you create an example design, the calibration IP is automatically configured and connected. Going back to the memory IP parameter editor, the option to create an example design project is separate from the main IP generation. The Example Designs tab in the parameter editor provides options specifically for how the example design should be generated. choose to create example design files and an Intel Quartus Prime project for synthesis, simulation, or both, and the preferred HDL language for simulation. If you disable both the simulation and synthesis options, only scripts to create the full example design will be generated. We'll discuss these scripts in a moment. If you're generating the example design to run on a development kit, select the kit here, if available for your target device, and make sure you've set the memory interface preset to the same kit as discussed earlier. The example design will have all assignments, such as pin locations, set specifically for the selected development kit, making it easy to get up and running quickly. Generating the example design is done through the Generate menu or the Generate Example Design button. In the Generate menu, the Generate HDL command at the top creates the files for just the IP itself, as listed earlier. To create the example design, instead, select the option shown in the Generate Example Design submenu, or click the Generate Example Design button. The directory name for the example design can be selected before generation. Once the example design is generated, simply open the edsynth.qpf project file in the Intel Quartus Prime software to start working with the example design. A .qsys file is also created and set as the top-level entity in the project. You can use this system as your main system design or as a subsystem design in a separate project. As mentioned, if either or both of the simulation and synthesis options are disabled on the Example Designs tab, only project generation scripts are created. Use this option to create the example design project later. The example design project for synthesis is generated by running the script named makeQII design.tickle, found in the location specified when you generated the example design. You can run tickle scripts by selecting the option from the Tools menu in the Intel Quartus Prime software or from the command line using the command shown. When the script is run, it generates a new folder named QII in the example design directory and creates the project in that folder with the edsynth.qpf and .qsys files. Here is a block diagram of the example design generated by the memory IP. You can see that it is similar to the example design generated for the old UniPHYIP IP. The traffic generator issues write and read commands to the external memory and indicates whether or not the written data was successfully read back. The separate calibration IP is automatically included as well to connect the I/O SSM to the memory interface for calibration. Unlike the old UniPHYIP's example design, this example design is built as a platform designer system with the interconnect fabric exposed. This makes it easy to add additional components using the provided .qsys file. You could also incorporate the example design system as a subsystem in another system design. Implementing the example design as a platform designer system makes its use much more flexible. Instead of adding the memory IP directly to an Intel Quartus Prime project, you can add it and the calibration IP as components in a platform designer system, as shown earlier. When you do this, the flow is slightly different for file generation. Add the Altera EMIF FM IP and Altera EMIF Cal IP to a system using the Platform Designer IP catalog instead of the IP catalog in the Intel Quartus Prime software. The IP parameter editor will open. All the parameters are the same as in the IP parameter editor described earlier. To create the example design just discussed, click the Generate Example Design button in the parameter editor and select a location for the files. You can also do this from the Platform Designer Parameters tab if the IP has already been added to a system. The other files mentioned earlier do not get created until the Platform Designer system is generated. You can generate the system manually in Platform Designer creating the .QIP file that must get added to the project, or add the .QSys file itself to the project to have the system generated at compile time. When the system is generated, it creates a folder with the same name as the .QSys file. In this folder is the .QIP file and additional folders containing the modules that make up the IP, as well as the standard synth and/or sim directories for compiling or simulating the design. See the Intel Quartus Prime Platform Designer user guide for details about what files get created when a Platform Designer system is generated. Intel Agilex System-on-Chip, or SoC devices, are FPGA devices that include an ARM Cortex hard processor system, or HPS. Including a hard processor along with an FPGA fabric allows for lots of options and customizability for both hardware and software design. The HPS can connect to and use a standard external memory interface as the processor's main memory. To do this, a variant of the Altera EMIF FM IP called Altera EMIF FM HPS must be added to an HPS system design. This IP, called External Memory Interfaces for HPS Intel Agilex FPGA IP in the Platform Designer IP catalog and located in the Hard Processor Components category, must be used instead of Altera EMIF FM. This IP has a special conduit connection, not available in Altera EMIF FM, that is required for the HPS to access the memory controller. This conduit must be enabled in the HPS parameter editor, as shown here on the right. The parameter settings and generation flow for the HPS EMIF IP are identical to the standalone memory IP. Once both the HPS and EMIF IPs have been added to the design, all that is required is to connect the conduits to each other in Platform Designer. An instance of the separate calibration IP is required as well. Due to the hardwired connections between the ARM processor and FPGA resources, there are some limitations on the options and configurations available for memory interfaces used by the HPS. HPS memory interfaces have limited placement options. Only a few subbanks located near the HPS on the device can be used. Also, the external pinout is set and fixed by the IP when the system is generated, including ECC signaling if enabled. It is possible to make some pin swaps, such as the data pins associated with a particular DQS strobe pair, but this requires manually editing both the Platform Designer generated .QIP file and the projects.qsf file while following a specific set of rules. When configuring the IP, note that you are limited to the full memory bus widths shown, and that the DQ width for a strobe is fixed to by 8. On-chip debugging features, discussed in another part of this training, are not available, though a workaround for this is discussed there. For more details on the restrictions and use of an HPS external memory interface, see the Intel Agilex EMIF IP user guide, as well as the Intel Agilex HPS Technical Reference Manual. To learn more about Intel FPGA SoC device architecture and hardware design, attend the instructor-led and online training classes linked here. As with other IP, once you generate Altera EMIF FM, you must specify some constraints for the memory design to guide its placement in the device. So what needs to be constrained for Altera EMIF FM? Well, not much actually. The new format of the .QIP file not only points to all the files that make up the IP, but it also includes all the constraints that were previously added by running a pinassignments.tcl script. This includes all I/O-related assignments except for exact pin locations. With this .QIP file, the I/O-related assignments are not written to the .QSF file and do not need to be written into that file. This is a new feature of the .QIP file. This feature also makes it easy to override the constraints in the .QIP file. Simply add the overriding constraints to the .QSF file. Any constraints in the .QSF file that match the .QIP file but have different values take precedence. So the only constraints really needed are exact pin locations. There are a number of ways to create the I/O location assignments that we'll look at in a moment. Before making location assignments, it's important to understand the pins associated with each I/O subbank and how the pin tables in the device datasheet are used. Recall that each I/O subbank has 48 dedicated I/O pins, separated into 4 I/O lanes of 12 pins each. The pin tables document the functions of each of the 48 pins in each subbank. Since the IP is hard, certain signal functions, such as the DQS strobes, clocks, and many of the address and command signals, have fixed locations. Each pin is indexed within each bank and the edge of the device as shown. The associated package ball is also listed. When manually choosing which subbanks you want to use for implementing an interface, you'll use the pin tables to select the correct locations for each signal. To obtain pin tables for your selected Intel Agilex device, please contact Intel FPGA. To make it easier to make the location assignments, the README file generated by the IP, mentioned earlier, provides an example pin placement table. The table does not specify specific subbanks in the device. It only shows how signals could be organized to implement the interface. The table shown here is for the DDR4 by 72 example shown earlier. As before, the design requires 3 subbanks. Notice the address and command signals in the center subbank taking up 3 I/O lanes. These are fixed function locations. The pin indices listed must be the locations that are used on whichever bank is used as the center subbank. The 9 bus groups, however, can be swapped around with each other, and the DQ pins in each group can also be swapped around within that group. The README file makes it very easy to create a pin layout for the design in whatever location on the device you specify. So with this information, you can choose the location for your memory interface and create the pin location assignments in 4 different ways. You can let the fitter make all the assignments, you can manually assign all of the signals of the interface to pins, or you can constrain only a few pins to specific locations and let the fitter place the rest. The final method is to use Interface Planner to easily create legal assignments using a graphical interface. While you don't have to add any pin assignments to your design, it's highly recommended, especially in designs with multiple memory interfaces. Including pin assignments can speed up compilation time, avoiding the need for the fitter to select pin locations for you. In the first method, the fitter selects all pin locations. This is the default method and is performed by simply compiling the design. The fitter will automatically select a particular subbank or group of adjacent subbanks and place all the signals appropriately, following all the placement rules discussed so far. If necessary for timing or other requirements, the fitter can swap bus groups with each other or data pins within bus groups. To use the pin placement selected by the fitter, simply back annotate the fitter assignments after compiling the design. This method is good for small designs and designs where you have the freedom to place the interface anywhere on the device. This method may not be a good solution for a larger design that uses lots of I/O-related IP. The other IP may overuse the device I/O pins in such a way as to prevent the fitter from finding locations for all the subbanks needed to implement the interface. This would cause a no-fit error. Method 2 is to manually assign all the signals of the interface to specific locations. To do this, choose which subbanks in the device you want to use. Then, using the device pin tables and the generated README file, make assignments to the correct indexed pin within each subbank. Recall that each of the 4 I/O lanes in an I/O bank consists of 12 pins. Also remember that the address and command signals have fixed locations in their I/O subbank and must be placed in those fixed locations. DQS and DQS pound signals have fixed locations in each I/O lane. For a by 4 group, there are 16 strobe locations in a subbank, 4 in each of the 4 I/O lanes. For a by 8 group, there are 8 strobe locations, 2 in each I/O lane. A by 18 group requires 2 I/O lanes, so 2 fixed strobe locations in one of the 2 lanes are used. The DQ pins associated with a particular strobe pair can be swapped around depending on the width of the bus group. For a by 8 interface, the pins can be swapped within the I/O lane. For a by 4 interface, where there are 2 bus groups in a single I/O lane, the pins can only be swapped within each of the 2 nibbles within the I/O lane. You can't swap pins between the 2 separate bus groups. For a by 18 interface, you can swap pins around between the DQ pins of either of the 2 I/O lanes. To create the location assignments, either manually make assignments in the .qsf file or use the pin planner. While this method gives you the most control over pin placement, it can be a long, tedious process to make sure all the assignments are correct. Method 3 gives you the best balance between fully automatic placement by the fitter and complete manual placement. Method 3 involves manually making a few key location assignments and allowing the fitter to make the remaining assignments. To use Method 3, first, as in Method 2, select the subbanks you want to use for the interface. Then, manually create only the required assignments listed. Only a single address command signal, such as memory clock 0, needs to be placed because all the other locations are fixed in the address and command I/O subbank. The fitter will automatically place the rest of the signals in the subbank where that single signal was placed. Select locations for the PLL reference clock and the RZQ pins, the only signals not directly associated with the rest of the address and command signals. Finally, place all the strobe signals. This will indicate which I/O lanes to use for the data bus groups. The fitter is then free to place the DQ signals in the correct I/O lanes in any order. As with Method 1, remember to back annotate the fitter assignments after compiling the design to write the fitter selected location assignments to the .qsf file. Here are some simple examples of assignments to add to the .qsf file for methods 2 and 3. Use the set location assignment tickle command along with the -2 option to specify the signal to assign. Select a specific pin location based on the device pin tables, or assign the signal to a particular bank, allowing the fitter to select a specific location. The final and perhaps easiest method for creating the assignments is to use Interface Planner, formerly known as Blueprint. Interface Planner uses the power of the fitter in the Intel Quartus Prime software on a synthesized design to analyze the I/O interfaces used and highlight only the legal resource locations for each interface, making it easy to quickly create assignments. In the example shown here, legal starting pin locations are highlighted on the package view of the device. The package view is similar to the pin planner. The main difference between the two tools is that I/O assignments are created in the pin planner one by one, while entire interfaces can be assigned to legal locations with a double click in Interface Planner. When selecting an interface, referred to as a design element in the tool, click the highlighted arrows in the Legal Locations column. Legal locations for the interface are listed on the right, and a starting I/O pin that will be used for that location is highlighted in the package view. The selection of legal locations by the tool takes into account all of the required resources and rules mentioned earlier, such as the use of I/O subbanks, lanes, the I/O SSM block, PLLs, and clock networks. Select one of the legal locations from the list to highlight the rest of the pins that will be used for the interface if it is placed in that location. When a selected legal location is double-clicked, the design element and all of its required I/O pins get placed at the location specified. You can then fine-tune individual signal placement, such as swapping around the data DQ pins for a particular DQS strobe pair, like in option 2 from earlier, but with the live legality checking performed by Interface Planner. As pin adjustments like this are made and more interfaces are placed in the chip, the placement rules are adjusted to take into account already placed design elements. In this way, you can quickly make assignments to an entire design, knowing the placement is legal before running a lengthy fit. You can also make design element assignments using the chip view, a view of the internal resources of the device, similar to the Intel Quartus Prime software chip planner. The same process for making placement assignments is used. Simply double-click a legal location from the list. Creating assignments in this view is useful if you want to assign an interface to certain I/O banks and subbanks. This is much easier than making pin assignments to the correct pins to select I/O subbanks, as was done in methods 2 and 3 discussed earlier. Once all design elements have been placed, Interface Planner outputs a Tickle script with all the assignments made in the tool. The assignments are only applied to the design once the Tickle script is sourced back in the Intel Quartus Prime software. This is just a taste of the features in Interface Planner. To learn more, register for the Fast and Easy I/O System Design with Interface Planner online training, linked here and at the end of this training. With the amount of resources available in Intel Agilex devices, implementing multiple memory interfaces in a single device is more useful than ever, but it's important to understand how the resources are used and how they can be shared among multiple interfaces. Let's take a look at this. Multiple memory interfaces can be placed in the same I/O row or in different rows. If the interfaces are in the same row, they can share certain device resources, allowing for the implementation of more interfaces or for freeing the resources up for other uses in the overall FPGA design. Most of the resources in a row of the device can be shared. This includes the I/O lanes, the I/O SSM block, the reference clock signals, and the clock networks. The only resources that cannot be shared are the memory controller, the PLL, the DLL, and the OCT block and its associated RZQ resistor. The controller cannot be shared because it must be dedicated to a particular interface. The PLL and DLL cannot be shared because their clock networks are dedicated to a particular subbank. However, the reference clock input to multiple PLLs can be shared in order to synchronize multiple interfaces. As for on-chip termination, it is recommended to use separate RZQ resistors for each interface, and thus OCT blocks must be unique for each interface as well. To implement shared device resources, you may need to change options in the IP's parameter editor, or adjust the pin location assignments appropriately, depending on what resources are to be shared. Here is an example of how the I/O lanes in a subbank can be shared between two interfaces. Two by16 interfaces can share the center subbank, reducing the subbank usage from 4 subbanks down to 3. In order to perform this kind of resource sharing, both interfaces must be the same memory protocol, such as DDR4, running at the same clock frequency. They must also use the same I/O standard and voltage, and use the same reference clock pin to drive the PLLs. You'll see how to do this in a moment. With this configuration, 2 lanes go unused in the center subbank. These pins can be used as GPIO, as long as they use the same I/O standard and voltage as the 2 memory interfaces. They must also be used as single-ended signals. As mentioned, reference clock pins can be shared as well. To do this, simply connect the reference clock input signal to the clock inputs of the multiple interfaces in the design's top-level RTL code. As before, the multiple interfaces should be placed in adjacent subbanks. Reference clock sharing is required for sharing multiple interfaces core clock networks. You may also want to share core clock networks. You might want to do this to reduce the number of global clock networks used in the design, or to avoid any latency caused by clock domain crossing logic between multiple interfaces. To share core clock networks, 2 or more interfaces must use the same memory protocol, run at the same clock frequency, and already be sharing the same PLL reference clock, as just discussed. Once again, the interfaces must be in adjacent subbanks in a row. To perform the sharing, a core clocks sharing option can be found on the General tab in the parameter editor for the memory IP. Setting this parameter to master or slave exposes clock sharing signals. Only one of the interfaces in a row can be set to master. The interface set to master will be the only one that has an input connection for the PLL reference clock and an output connection to connect to the slave interfaces. The slave interfaces will only have a clock input signal that must be attached to the master's output clock signal. You can connect the master's output clock signal to multiple slave interfaces, or enable the option shown to daisy chain the clock through multiple slave interfaces. The implementation is identical in both cases, but daisy chaining may be easier to represent and implement when creating the design using the Platform Designer GUI. Note that even though each interface will still have its own unique output clocks to drive user logic, these output clocks are identical when the core clock networks are shared like this. As such, you can use a clock from either a master or slave interface to drive your user logic without requiring any additional clock crossing logic. This concludes part 2 of the training. If you'd like to continue the training or see part 1, you can register for parts 1, 3, and 4 for free at the links shown here. To learn about additional resources available to help you in implementing an external memory interface, continue to the next slide. There are many resources available to help you with memory interfaces in Intel Agilex devices. The documentation resources listed and linked here should be the first ones you visit. The EMIF Support Center and the EMIF IP User Guide are your one-stop shop for all things EMIF related. Besides documentation, there are many training classes available from Intel FPGA on memory interfaces, Platform Designer, and Interface Planner. The Platform Designer classes listed here will show you how to incorporate a memory interface into a complete system design. The Interface Planner online training goes through the basics of what the tool is and how it works, along with a demonstration of its use in the placement of an external memory interface. Intel FPGA provides many additional technical support resources besides technical training. Check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Visit the Intel FPGA Wiki for design examples and up-to-date articles written by field application engineers. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on high-performance memory interfaces in Intel Agilex devices.